Hi, welcome to this third video in the mini-series all about E, where we're discussing the number E and its relationship to real exponentiation. In this video, we will prove that E is a transcendental number. Here's the outline of topics we will discuss in this video. So first, we're going to discuss a brief proof that E is irrational, and then we're going to sketch the main idea of the proof for E being transcendental. And that proof is going to be motivated by the structure or the main idea of the irrationality proof, which is why we're even doing the irrationality proof in the first place. And then finally, we'll go to the whiteboard and give a fully detailed proof that E is transcendental. Before we dive into the content, let's discuss the main prerequisite facts that we're going to be making use of for this video. Here are the main prerequisite facts that we're going to be making use of for this video. So the first fact is really just an application of integration by parts, and the second fact is a generalization of the product rule for derivatives. So we'll address each of these in turn, starting with this first fact. So this first fact is really just a formula for this integral on the left-hand side that you see here. So the integral is from 0 to x, where x is a variable upper bound on the integral, of the function e to the negative t times f of t dt, where f is just any differentiable function. And what this works out to be, if you do integration by parts, is it works out as f of 0 minus e to the negative x times f of x, plus the integral from 0 to x of e to the negative t times f prime of t dt. Now, the way that you see some structure on this right-hand side is that you notice that this middle term that's being subtracted off has the same form as the integrand on the left-hand side here, and the integral on the right-hand side is the same thing as the integral on the left-hand side, except that we've replaced the function f of t with f prime of t. So in practice, if we wanted to evaluate this integral on the right-hand side, we could use this same formula all over again, now just replacing f with f prime. That's assuming that f prime is itself differentiable as well, but for our purposes that will be true. So anyways, you could imagine just iterating this formula over and over again with the integral now involving f prime, and then the next time it would involve f double prime, then f triple prime, etc. And at some point you just kind of intuitively think that f prime is simpler than f double prime is simpler than f prime, and as you take more derivatives, the function gets simpler, and so these integrals at some point will become easy enough to solve directly, and then you'll be able to get some closed form expression for this initial integral from the left-hand side. And then the second fact here is, as mentioned, a generalization of the product rule for derivatives. So first of all, if we have a function f of x equals a product of functions a of x times b of x, well, we know how to differentiate this function using the product rule for derivatives. But if we want to take the nth derivative for any n, then this is the formula that we're going to require. So what it works out as is the nth derivative of this product of functions is the sum from I equals 0 to n of the coefficients in front of n choose I, and then times the ith derivative of the a function times the n minus ith derivative of the b function. And you're taking these terms and you're summing them all together from I equals 0 to n. And so first of all, this is called the general Leibniz rule, and you can notice that this is completely analogous to the binomial expansion formula that we're familiar with, where you have these coefficients and then there's some convolution going on here. But anyways, so we'll make use of this formula as well. So both of these formulas, it's not hard to prove them. You can use integration by parts for the top one and induction for the bottom one, but that's not really our focus right now. We're just going to make use of these formulas in our proof that E is transcendental. Probably the most important prerequisite concept is the definition of being a transcendental number, and we're going to be proving that E is a transcendental number, so it might help to know what transcendental means, first of all. First of all, a number is algebraic if it is the root of an integer polynomial. So here are some examples of algebraic numbers. The cubed root of 7 is an algebraic number because it's the root of the polynomial x cubed minus 7. And this is a polynomial with integer coefficients. That's what an integer polynomial is, by the way. It's a polynomial with integer coefficients. So This is certainly an integer polynomial, and cubed root of 7 is obviously a root of this. So that makes cubed root of 7 an algebraic number. Similarly, 2/5 is an algebraic number because it's the root of the polynomial, of the integer polynomial 5x minus 2. 10 is an algebraic number because it's the root of the integer polynomial x minus 10. 1 plus root 5 over 2, that's, by the way, that's the golden ratio, phi. And this is well known to be the root of x squared minus x minus 1, which is, again, an integer polynomial. And then finally, I, of course, we all know that that is the root of, or a root of x squared plus 1. So these are all integer polynomials, and these were all roots of those things, so that makes all of these algebraic numbers. Now, a number is transcendental if it's not algebraic. So in other words, if it's not the root of any integer polynomial. So basically, you can split up all the numbers, and by all the numbers, I guess what we should really mean is all the complex numbers. We can kind of break them up into algebraic and transcendental. So all these numbers live in this part of the complex numbers, and other numbers live in the transcendental part, for example, e. So it's worth asking if any transcendental numbers exist at all. Maybe every number is the root of some integer polynomial, but as we're going to show, that's not the case. In particular, e is not going to be the root of any integer polynomial. So this is really the most important concept that we'll need is just what it means to be transcendental, of course, because in our proof, we're actually going to be assuming that e is algebraic instead, and we'll get a contradiction. But anyways, we'll get there when we cross that bridge, so this really just concludes for now all the prerequisite concepts that we needed for this video. So as previously mentioned, the first thing we're going to do is to prove that e is irrational, and we use this proof as a bit of motivation for the proof that e is transcendental. So let's go ahead and prove this then. So the first thing we'll do is introduce some notation. So e sub n of x, this is going to be the partial sums for the Taylor series of the exponential function. So so the n is this n here is indicating the nth partial sum. So we have the sum k equals 0 to n of x to the k over k factorial. So in other words, if we took the infinite sum here, that would be the exponential function, but we're just truncating the sum, stopping at the nth term here, and that's what this function is. And then e sub n, that's going to be shorthand for e sub n evaluated at 1, at x equals 1. And so, of course, if you plug in 1 to the Taylor series expansion, the infinite sum here, you'd get exactly e. When you plug in 1 to the nth partial sum here, you get some approximation of e. Okay, so what we do then is we look at the difference between the approximation of e and e itself exactly. So e itself is going to be the infinite sum, e sub n is the partial sum. Looking at that difference, we have this, the infinite tail is what's remaining. Once you take away the first n terms of the series, you're left with the infinite sum here, k equals n plus 1, all the way off to infinity of 1 over k factorial. So that's the difference. And now we're starting with 1 over n plus 1 factorial, then 1 over n plus 2 factorial, 1 over n plus 3 factorial, etc. So what we can do is we can factor out an n plus 1 factorial out of the denominators. So let's factor out a 1 over n plus 1 factorial out of everything. And then what's left in the infinite sum here is the first term would be 1, the next term would be 1 over n plus 2, the next term would be 1 over n plus 2 times n plus 3, because we're just, of course, that's what k factorial is doing. It's growing the number of terms being multiplied together, and we've just taken out the first n plus 1 of them in this factor here, so it's just the rest now. So the next term would be 1 over n plus 2 times n plus 3 times n plus 4, and you get the idea. So it goes on forever like that. And now what we can do is we can bound this quantity here, because for each of these individual denominators, we can decrease them. So let's decrease them all to n plus 1. So each of these terms, n plus 2 is going to become an n plus 1, n plus 3 will become an n plus 1, everything becomes an n plus 1. And so that will give us 1 over n plus 1 factorial times this quantity here. So 1 plus 1 over n plus 1, that's what n plus 2 became. then n plus 2 times n plus 3 becomes 1 over n plus 1 squared. Then the next one would become 1 over n plus 1 cubed, etc. And so what happens, we're making each of these denominators smaller, which is making the overall ratios here, they're all getting bigger. So the overall sum's getting bigger. So that's why we're able to do an upper bound like this. So this is the upper bound. And the point of doing this is because now you see here we have a geometric series where the common ratio is 1 over n plus 1. And so then using the formula for a geometric series, we have 1 over n plus 1 factorial times, that formula gives us 1 over 1 minus 1 over n plus 1. And simplifying that, it works out to be 1 over n factorial times n. So what we've just done is we've just shown that this difference here is bounded above by 1 over n factorial times n, which is not very big. So far what we've shown is that this difference, e minus e sub n, is smaller than 1 over n factorial times n. So we mentioned that was not very big. Actually, that's quite an understatement. It's extremely small. So what that means is that e sub n is doing a great job approximating the true value of e. If you recall from the previous video, if you watched that, where we were doing some sage computations, what we noted there is that we had fast convergence of this this e sub n quantity. We were using that. We were using the partial sum Taylor series to get a value, to get an approximate value for e, and it was converging so fast. And this kind of explains why. We have a small error here. If we treat the difference of the true value of e and the approximate value of e as being the error term, as we're showing here, it's quite small. And so that's really why we were converging so quickly to the true value of e without making n very large at all. It's because we have this n factorial in the denominator here in particular. Anyways, so going on with the proof, we want to prove that e is irrational. So what we're going to do is suppose for contradiction e is a rational number. So in other words, that e is some integer fraction, so a over b for some integers a and b. Then what that means is that if we look at this modification of the error, where we take the error here, e minus e sub b times b factorial, so that's what we multiply by, that has to be an integer, and it's a non-zero integer. So first of all, b, that's the denominator of this supposed fractional representation of e that we claim exists. So that's the b that we're using here. And so b factorial times this is an integer. Why is it an integer? Because if you think about everything going on in this term here, so e, we're claiming it's a over b. So obviously b factorial is going to clear out that denominator for e then. It's going to be some integer then for b factorial times e. And it'll be similar for e sub b, because e sub b, that's the sum of 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, etc., all the way up to 1 over b factorial. And this b factorial is going to clear out all of those denominators, leaving us only with numerators, all of which are integers. And so therefore, the entire thing then with this, this product overall is an integer. And so that's what we're claiming here. And it's not zero simply because b factorial isn't zero, and neither is this error term. So it must be some other non-zero integer. Okay, but the problem is that, on the other hand, we just established this bound for the error above. It was so small that even when multiplying by b factorial, we still have that, if you look up here and replace n with b, we would have this difference. It's 1 over b factorial times b. So multiplying by b factorial, as we're doing now, that's less than 1 over b using that bound. So we have, it's a positive number, of course. Everything in here was positive. So we have some positive integer, but it's less than 1 over b, which is some fraction, which is less than 1. So what integers are there that are strictly between 0 and 1? None at all. So that's a contradiction, and that ends the proof. So that shows that e can't be a rational number. So the main takeaway then is that the error is so small that some modification of that error must must simultaneously still be a small yet also non-zero integer, which is impossible. So it's still small because the original error was just so small that kind of inflating it still didn't make it too big. But at the same time, we showed that it had to be some integer value, and you can't have something that's small, which is basically fractional. You can't have that be an integer unless it's zero, but it's not zero either. So you get some contradiction like that, and so that's really what the key idea to take away from this proof is, because we're now going to be proving a more general fact that E is transcendental, but we're actually still going to be making use of this kind of key idea here in that proof. Okay, so finally, let's sketch the main idea of the proof that E is transcendental. So the idea will be basically the following. We're going to suppose that E is not a transcendental number. So in other words, it's an algebraic number. So by definition then, that means it's the root of some integer polynomial. So here would be that polynomial where we've already plugged E in for that polynomial. So sum k equals 0 to n for some n, the coefficient c sub k times the powers e to the power k. So e being a root for that polynomial, it means this is going to evaluate to 0 when you plug in e. And so this is just for some choice of coefficients c sub k that are integers and a minimal n, where n would be the degree of this polynomial. And so potentially there could be many polynomials, integer polynomials, which have e as a root. So the degrees of some of those polynomials might be bigger than the degrees of others. So let's just take a polynomial which has e as a root where n is as small as possible. So smallest possible degree integer polynomial. And so then what we'll do based off of that is we're going to devise some rational approximations of these powers of e in some way or another. We're not going to elaborate here, but of course we'll go into the details when we do the proof. And so we'll express these rational approximations. E to the power k, it'll be a to the k over b. That'll be the rational part. And then there's going to be some leftover error here. That'll be epsilon sub k, also over b. So b is going to be a common denominator for every k. It'll be the same denominator. And a sub k and b, those are all going to be integers. And so this is the rational part plus some compensating extra part to get us all the way to the true value of e to the power k. And when you plug this representation of e to the power k into this polynomial, what's going to happen is that a part of the polynomial is going to become sum k equals 0 to n of c sub k times the epsilon sub k's. And the errors of these epsilon sub k's, they're going to be so small that that part of the polynomial there will still be small. Yet it's also going to be, we're going to show that it's some non-zero integer, just in the way that we did before. We had some error for the irrationality proof, but we showed that simultaneously that error had to be an integer and it had to be very small and not zero, so that gave us a contradiction. It'll be the same story here. So that's going to be the structure of the proof for us. So now that we've established this, let's actually head to the whiteboard and we'll work out the proof that E is transcendental in full detail. Okay, so here we are at the whiteboard, and now we want to start the proof for showing E is transcendental in the manner that we mentioned on the slide that we copied over here, where we want to give rational approximations of the powers of E. So e to the k, we said that's going to be approximately a sub k over b, where a sub k and b are integers. So that's a rational approximation of e to the k. And so it's e to the k is going to be exactly equal to a sub k plus some error, epsilon sub k, and then all of that over b. And this, by the way, is for all k. And b is independent of k. So then what we do is we're going to be taking this expression for e to the k, and we're going to be plugging it into the polynomial for which we're assuming it's a root of. And then we'll get some contradiction from there based on the error being too small in a similar manner to the proof of irrationality. But anyways, right now the major question is what are these terms? What is a sub k? What is epsilon sub k? And what is b? And so first we need to work towards that. The way that we're going to do that is we're going to make use of the following identity here for polynomials. So we're going to say let f be any polynomial, and then we'll have the following equation is true for polynomials. We'll have e to the power x times the integral from 0 to x of e to the minus t times f of t dt. Now this is the integral that appeared from the prerequisite facts, if you notice, so that'll become relevant in a moment. But anyways, this equals e to the power x times the infinite sum from I equals 0 to infinity of all the derivatives, the ith derivative evaluated at 0, and then minus the infinite sum from I equals 0 to infinity of all the derivatives, so ith derivative evaluated at x, where again x is just the variable upper bound on the integral. Okay, and so this looks a bit scary when you first look at it because we have these infinite sums here, but keep in mind that f is a polynomial, and so when you differentiate a polynomial sufficiently many times, it's going to vanish completely. So for example, if f was a cubic polynomial, then by the fourth derivative, it's going to be identically 0 from there on up. So it looks like an infinite sum, but actually it's a finite sum because f is a polynomial. Now, how do we derive this formula? Well, let's just, we're going to make use of the formula that we introduced in the prerequisites. So let's just recall what that was. It's the integral from 0 to x of e to the minus t times f of t dt. It equals f of 0 minus e to the minus x times f of x, and then plus the integral from 0 to x of e to the minus t times f prime of t dt. And this was true for any differentiable function at all. Now, in particular, we're going to be using it for f being a polynomial, so it's going to be infinitely differentiable in particular. So using this formula, we're just going to iterate this formula using it over and over again, because now you see that this this left-hand side, or sorry, this right-hand side integral is the same form as the left-hand side, so we can use the formula all over again, just replacing f with f prime. And so that integral is equal to f prime of 0 minus e to the minus x times f prime of x, and then plus the integral from 0 to x of e to the minus t times f double prime of t dt. So we can do this. We're assuming that f is infinitely differentiable now. And so, so again, you can see we can just apply it all over again. So what's that integral now? Well, that's the, it's going to be f double prime of 0 minus e to the minus x times f double prime of x plus the integral from 0 to x of e to the minus t times f triple prime of t dt, and so on. And so you could ask, well, we could just keep doing this over and over. When does it stop? Well, the answer is it stops once this, this function, this derivative vanishes. Because, again, f is a polynomial, so upon some derivative, it's going to be completely 0. So let's just, for the sake of concrete assumption, let's just say that f was a cubic polynomial. Then by the fourth derivative, it would be 0, and the integral would go away. So at some point, these integrals stop appearing, and you're just left with a finite sum. And it's a finite sum of what? Well, as you can see, what you have is an f of 0, an f prime of 0, an f double prime of 0, and so on until at some point this is going to stop. And so you'll have a sum of those things. Okay, so we'll just close that up. And then we're subtracting off e to the minus x times f of x, f prime of x, f double prime of x, and so on. So that'll keep going for a while. So we'll just put some dots here to indicate that we could keep adding more. And these integrals, we're expanding them all out. That's what's giving rise to the, to these terms and so on. So we're not adding any integrals together. I mean, that's what's already been done by iterating this this formula that we had. So in total, what we have is we have the sum of all that, from f of 0, f prime of 0, f double prime of 0, all those things you see that we can rewrite that. That is equal to the infinite sum, I equals 0 to infinity, of all the derivatives evaluated at 0. And again, that's because at some point we're just adding zeros, because at some point the derivatives of f vanish. So we're allowed to do this infinite sum. And then we're subtracting off e to the minus x, and we just factor that out of the infinite sum from I equals 0 to infinity of all the derivatives evaluated at x. So that is what that initial integral worked out to be in the case when f is a polynomial. So this formula, when f is a polynomial, that integral becomes this quantity down here. So now, just multiplying both sides by e to the x, you see that what we would have is that we would have an e to the x here. We'd cancel that e to the minus x, and then we'd have an e to the x in front of the integral, and then finally you see that gives you this exact formula which we asserted just a moment ago. So that's how you would derive that formula. And just for some notation, we're going to take this infinite sum here. We're going to call this capital F evaluated at 0. Okay, so the capital F, that's going to be the infinite sum of all the derivatives of little f evaluated at 0. And so similarly, and more generally, capital F of x, that's the infinite sum of all the derivatives of little f evaluated at x. So we can re-express our formula one last time. We can rewrite it as e to the x times the integral from 0 to x of e to the minus t times f of t dt. This equals e to the x times f of 0 minus capital F of x. And this is really the version of the formula that we're going to be making use of in our proof. So what's the purpose of this formula that we've established now? Well, you notice that what we can do is we can solve for this e to the power x here, and we're also going to replace x with the integer k. So x could be any real number. We're just going to replace it with k to be suggestive of the fact that we want an integer here now. Now solving for this e to the x right here, this power of e, we'll have e to the power k now, because we're replacing x with k, and that's equal to e to the k times the integral from 0 to k times of e to the minus t times f of t dt, and then plus f evaluated at k divided by f evaluated at 0. Now, you do need to be careful that this denominator is non-zero. As we'll see later on, it will be non-zero, so this division is totally safe to do for our purposes. Now, the purpose of doing this is that, if you recall above, we just said that we wanted this e to the k to be able to be expressed as something like this, where it's some ratio, some rational number, a sub k over b, and then plus some error, epsilon sub k. And so that's actually what we're going to be able to achieve with this form right here. Actually, we've written it the wrong way around, but this part here, so f sub k, that's what's, so that'll be a sub k. So a sub k is equal to f of k, and then down here, b is going to be equal to f of 0. And then finally, this final part, I won't rewrite it, but this part here, this will be epsilon sub k. That'll be our error term. And so this is all high level right now, because keep in mind, we don't know what capital F is in particular, and capital F is determined by little f, and we haven't made a choice for little f yet. All we're saying is it's going to be some polynomial, but we haven't chosen the polynomial yet. Once we make that choice, that will determine the integral and capital F, and hence this entire expression here. So that'll all be made explicit momentarily, but right now we're just talking about the high-level format of all this. So the purpose of this, as mentioned, was now we are able to express powers of e sub k in this way. So if we look at the polynomial that e is supposed to be a root of, it's the sum k equals 0 to n of c sub k times e to the power k. And now we have this replacement for what e to the power k is. So this is equal to the sum k equals 0 to n of c sub k times So first of all, times f of k over f of 0, that's the rational part, and then we'll separately sum k equals 0 to n of the error term, epsilon sub k, over f of 0. And then, of course, times c sub k in front, obviously. Now, all of this is equal to 0, because remember, this is the polynomial that e is supposed to be a root of. So, so e being algebraic would make it a root of this polynomial, and so this is 0. And if we just clear out the denominators, we'll multiply everything. So multiply by f of 0. Then we'll go down a step here. What we have is the sum k equals 0 to n of c sub k times f of k, and then plus the sum k equals 0 to n of c sub k epsilon sub k. And this is also equal to 0. Now, taking a seemingly arbitrary step here, we're going to split this sum up into two parts. So this is going to be the sum c sub 0 f of 0 plus the rest of the sum, which is k equals 1 to n of c sub k f of k. And then, of course, plus the rest. So k equals 0 to n of c sub k epsilon sub k, and that all equals 0. And the point of splitting it up like this is that this middle portion here, what we're going to show is that this is going to be an integer, and it's going to be a multiple of some prime number p. Now, we're not saying what prime number it is right now, or even that it's an integer. We're just giving a high-level overview of what's going to happen. Just giving the structure of it right now. But it will end up being some integer multiple of some prime number. On the other hand, this portion here will also be an integer, but it will not be a multiple, so not a multiple of p. Overall then, what happens when you add together two integers, one of which is a multiple of p and the other of which isn't? Then overall you have another integer which is not a multiple of p, and in particular this will be an integer which is not 0. So that follows from the fact that adding two integers together, one of which is a multiple of p and the other isn't, then it's forced to be the case that you get another integer which is not 0. However, this portion here will show that it's not an integer because this is the error term. And so this error, we're going to show that in absolute values, this is going to be small, and in particular, it's going to be strictly less than 1. Now, we're going to have some non-zero integer plus some other portion, which is strictly less than 1, and we want that to equal 0. That's going to be a contradiction. So that's what we're going to derive as a contradiction in this proof. So really the proof is going to boil down to picking a particular polynomial f of x which has the properties that we want, such that when you go to this capital F of x, which is determined by little f, then when you look at this formula here, you get exactly what we're talking about right now. That you get that, this one part's an integer multiple of a prime number, the other part isn't, add them together, and then the rest is an error term, which is too small to get you to 0. And we'll see our contradiction. So this will be the structure of the proof. Now we're going to move on to actually determining what this polynomial little f of x actually is. Well, if we're trying to come up with this proof in the first place, we would be fumbling around in the dark for a while trying to reverse engineer some polynomial f that satisfies the properties that we want. But luckily we're not trying to invent this proof, we're just going through a well-established proof, and what's already established is that the polynomial which is appropriate to take is the following: x to the power p minus 1, so more on the number p in a moment, but then you multiply by x minus 1 to the power p times x minus 2 to the power p, and keep going like this all the way to x minus n to the power p, and then all of that divided by the number p minus 1 factorial. So p, first of all, p is going to be some prime number, and we don't know what that prime number is just yet. That's going to be determined more or less at the end of the proof when we need to choose a sufficiently large prime number. So we'll make that choice later on. So just to be clear, f is determined by the prime number p. But as of right now, we don't know which prime number p we're going to be choosing. And also, take a look over here at this number n. this is the number n that is the degree of the polynomial for which e is a root of. So we said that e is the root of the polynomial k equals 0 to n of c sub k x to the power k. And so when you plug x equals e into this polynomial, you're supposed to get 0. This is not the polynomial f. This is, just to be clear about this, I mean, not that we would have said anything that suggested otherwise, but just to make sure everything is separated in your mind, we'll call this some other name. We'll call this g of x, let's say. So g of x is the polynomial for which e is a root of, and that's not the same thing as f of x. F of x is just the polynomial which is going to give us the properties that we want to establish, as already mentioned here. And what are those properties? Well, it's what we've already mentioned up here. So let's just give them labels now so that we can concretely tackle them. So this will be number 1. That's property 1, property 2, and property 3. Now what we mean by those labels is, for number 1, what we're going to be showing is that c0 f of 0 is not a multiple of p. So it is an integer, but it's not a multiple of p. For part 2, we're going to be showing that that sum ckfk for the indices k equals 1 to n, that's an integer which is a multiple of p. And then that final part, the sum of the error terms, that's going to be something which is truly an error in that it's very small. It's going to be less than 1 in particular. And so putting those three things together will give us the contradiction that we've already discussed. So now we're just showing that this choice of the polynomial f is going to establish these three properties. So let's come down here and actually start with property 3. We could start with anything, but it might make the most sense to start with the justifying the notation of the epsilons. That is, we're going to show that the epsilons are actually small, which demonstrates why we're even notating them with epsilons in the first place. So specifically, what we want to show is that the sum k equals 0 to n of c sub k times epsilon sub k in absolute values, that's at most strictly less than 1. So that's the first part of our contradiction that we're going to derive. So how do we prove this? Well, we're actually just going to be looking at the quantity epsilon sub k itself. So we're going to see that this is actually a truly small error term. So the way that we see that is we just compute what it is, and we put a bound on it. So recall that epsilon sub k, this is e to the power k times the integral from 0 to k of e to the minus t times f of t dt, where now we actually know what this function f of t is. So we know that the function is, well, given above here. It's this function right here. And now that we know what the function is, that completely determines this entire quantity. So we know what epsilon sub k is explicitly now. So now how do we actually go about bounding this in the appropriate way? Well, it's not so difficult. What we do is, the first thing is just a very easy bound. E to the minus t, if we're over the interval from 0 to k, we can replace e to the minus t with 1. It's always going to be at most 1. So we can establish an easy upper bound by just saying this is e to the k times the integral from 0 to k of 1 times f of t dt. So in practice, all we're doing now is we're just computing the integral here. Now, what is the integral of this function f? Well, it doesn't really matter what the precise integral is. The way you can bound any function, the integral of any function, is say this is your interval from 0 all the way up to k here. What you do is the integral, of course, is just the area under the curve. Now, the easy upper bound you can establish is you just take the maximum, or the supremum of that function, really, over that interval, and then you just take the rectangle that generates. And so it has width of the interval, but height of the maximum value of the function. And that gives you a rectangle whose area is necessarily at least the amount of the area under the curve. So you can just see that geometrically very easily. So quantitatively, how that works out is we can say this is less than or equal to e to the k times the area of that rectangle. And the area is the width, which is k, times the height, which is the supremum of this function f of t over that interval, so t in the interval from 0 to k. So this is the quantity that we can say is an upper bound. Now, what is k? Remember, k is an index. It's running from 0 all the way up to n, where n is the degree of the polynomial g. And what we can do is we can just replace k with n. So k, the index k is going to be at most n, and it actually makes sense then to make another upper bound here. This is at most e to the power n times the supremum of the function over the interval from 0 to n. So clearly the exponential function itself, e to the power n, that's going to be bigger than e to the power k when k is an index, which is at most n. Obviously, k itself is less than or equal to n, and then the supremum over the interval 0 to k is at most the supremum over the interval 0 to n, because if you're increasing the size of the interval, then the supremum can only go up. So that's why we can establish this as an upper bound by replacing k with n. And finally, what is the actual supremum of this function? Well, we're not going to say what the exact supremum is. We're going to give an upper bound on this quantity as well. So we'll say this is less than or equal to e to the power n times n. And now if we recall what the function is, so the function is f of x equals x to the p minus 1 times x minus 1 to the p, all the way, you keep multiplying like this, all the way out to x minus n to the power p. And then that all gets divided by the number p minus 1 factorial. So an upper bound on this function over the interval 0 to n, which will then necessarily be at least the supremum, what we can do is, first, we can just replace x to the p minus 1. That gets replaced with an n to the power p minus 1. We, of course, can't go any larger than that over the interval 0 to n. Now, x minus 1 to the power p, we can replace that with an n to the power p. And we can similarly do that for every product of x minus I to the power p. So we keep doing that all the way, so n to the p. And there was n terms up here that were of that form. So we had x minus I, where I was the index 1 up to n. And so correspondingly, there's n products here of that form as well. So there's n of these. And we should still divide by p minus 1 factorial. Just keep that consistency there. Okay, so this is very clearly an upper bound. And so just kind of simplifying this, we can rewrite this as n to the power p, that to the power n, and then this n times this n to the p minus 1, we can just kind of put that all together and just say that's an n to the power p. And then, of course, now you see we have an n to the power p times n to the power p to the power n. So this just becomes n to the power p to the power n plus 1. And then lastly, let's just rearrange these exponents, which we have shown before we can algebraically do. So this is n to the power n plus 1, and that to the power p. Now, the reason for doing all this is that you see that what we have here is something which is exponential in p on top over something which is a factorial of p on bottom. So when n is a fixed number, and n is a fixed number, of course, p is the thing that's arbitrary here. And so what we do is we just let p go off to infinity. And so when p goes off to infinity, the denominator dominates the numerator. And so therefore this entire quantity goes to 0. That's, by the way, including this e to the power n out front. That's just a constant with respect to p. So again, remember, p is an arbitrary prime, and since there's infinitely many primes, it does make sense to take a limit of primes going off to infinity. So this is a well-defined limit, and then clearly this does go to 0 then. And so what that shows is that we've just established this upper bound on epsilon sub k. That was for every k, and that upper bound tends towards 0 as you make the prime larger and larger. And so therefore what we can conclude is that epsilon sub k is going to 0 as the prime, which epsilon sub k depends on, goes to infinity. Now at this point, it should be intuitively pretty clear why the sum k equals 0 to n of c sub k epsilon sub k should also go to 0 if we can make the epsilons as small as we'd like. But just to be explicit about this, we can put this in absolute values, and then the triangle inequality will give us that this is smaller than the sum k equals 0 to n of the absolute value of the ck's times the epsilon k's. We could also put the epsilon k's in absolute values, but that's just redundant since the epsilons are already positive. And this is, we could write this out. This is the absolute value of C0 times epsilon 0 plus absolute value of C1 times epsilon 1 all the way off to absolute value of Cn times epsilon n. Now, the reason I'm writing it like this is because one of these terms is the largest. We don't know which one it is, but it's certainly one of them. So let's just say that whichever one's largest, we'll call that the maximum, obviously. And there's n plus 1 terms here total, because we go from 1 to n, but also we have index 0 as well. So we'll say this is less than or equal to n plus 1 times the maximum of those values. So this is n plus 1 times the max of the absolute value of ck times epsilon k. And so that's the index k is ranging from 0 to n, of course. And now, for whichever k we ended up picking, that epsilon k, of course, it goes to 0 as you let the prime, which it depends on, go to infinity. And that sends the entire quantity here, which is fixed, besides for the epsilon, that sends the entire quantity then to 0 as well. And so that shows that the overall sum goes to 0 as the individual epsilons go to 0. So in particular, this is strictly less than 1 as long as you choose a sufficiently large prime. Okay, so that proves the first item, or as we numbered it, item number 3 here. And so now what's left to do is we want to prove these following two facts, which are that f of 0 times c0 is not a multiple of the prime number p that we're concerned with, and the sum of the ck/fk's is a multiple of the prime p that we're concerned with. So that'll finish the proof. So let's get going with those two items now as well. All right, so next we're going to show item 1, which says that c0 times f of 0 is an integer, but it is not a multiple of the prime p that we're going to choose. So as of right now, p is still arbitrary, but we're going to choose it in a way that guarantees that this quantity here won't be a multiple of it. So we'll see how that's done down below. So let's just go back down to the white space here. So item 1 now, what we're going to show is that c0 times capital F of 0, we'll say, is not in integers, the integer multiples of p. So that's notated with p times the set of integers. And we're saying that c0 times f of 0 is not in that set. So in other words, it's not a multiple of the prime p. Okay, so the way that we're going to prove this is it's actually going to suffice to show that f of 0 alone is not in the integer multiples of p. And the reason that that's true is because, well, what happens if we show that f of 0 is not a multiple of p? As of right now, p is still arbitrary, and so what we'll do is, since c0 is a constant, we'll choose p to be larger than c0, strictly. Actually, larger than the absolute value, just in case c0 happened to be negative. But anyways, it'll be larger than the magnitude of c0, and that way, there's no way that c0 could be a multiple of p either. And so you have a product of two things, c0 times f of 0, neither of which are a multiple of p, once you've shown that f of 0 is not. So then that product also cannot be a multiple of p because p is a prime number. So that's how we'll choose our prime p later on, so that it satisfies the fact that, so we'll just say here in parentheses, choose p so that it satisfies p being greater than the absolute value of c0. That way it's sufficient to just prove that f of 0 is not a multiple of p. All right, so let's compute what is f of 0. Well, let's just remember, by definition, this is the infinite sum, I equals 0 to infinity, of all the derivatives of little f evaluated at 0. Where again, remember, this little function little f here is x to the p minus 1 times x minus 1 times x minus 2 times all the way to x minus n, and those x minus somethings, those are all raised to the power p. So we just kind of factor that exponent of p outside. And then anyways, this is all divided by p minus 1 factorial. At first glance, it seems somewhat intimidating, actually very intimidating, to try to take derivatives of this function f, but we're now going to see why this function f was chosen to be what it is. Because while it's true that it's hard to compute derivatives, not only the first, but we also need the second, third, fourth, and arbitrary derivatives of this f function, we only need to evaluate them at 0, and that's going to make all the difference. So the way that we do this is, it's still a bit tricky, but you just have to be a bit clever about it. What you do is you split this function f into two parts. The first part that got circled, and then the second part. And so we're going to call that first part a of x, and the second part, that'll be b of x. So the function f is going to be a product of a times b. And so what that means then is we introduced the generalized Leibniz rule in the prerequisites. This allows you to compute the arbitrary derivative of a product of functions. So using the generalized Leibniz rule, we can express the ith derivative of the function f evaluated at 0. This is going to be, so this will be using the generalized Leibniz rule. And so this is going to be the sum from m equals 0 to I, so m is a new index, of binomial coefficient, I choose m, times the mth derivative of the a function evaluated at 0, and then times the I minus mth derivative of the b function evaluated at 0. And the advantage to having broken it up in this way is that notice that the a function in particular is especially easy to compute the derivative of. So just to be clear, a of x, that's x to the p minus 1 over p minus 1 factorial. So in other words, it's just some power of x divided by a constant. So in fact, no matter what derivative of this function you take, once you plug in 0, the output is also 0. That's always going to be true, except in the special case when you differentiate exactly the number of times that the exponent p minus 1 is. So if you differentiate p minus 1 times, then and then only will you have that the derivative p minus 1 times would be p minus 1 factorial on top, and then divided by p minus 1 factorial on bottom. So that's what the p minus 1 derivative of the a function is. And in other words, that's just 1. So if you differentiate less than p minus 1 times, then when you plug in x equals 0, the term vanishes. If you differentiate more than p minus 1 times, then the fact that the exponent is only p minus 1 means that the entire thing vanishes anyways, because the degree was less than the number of times you differentiated. So in the unique case, when you differentiate exactly the number of times that the degree is, p minus 1, that is when you get this number 1. So what we can summarize this as is, we'll say the mth derivative of a evaluated at 0, this is going to either be 1 in the special case that m equals p minus 1, and it's going to be 0 otherwise. And this really simplifies the summation above here, because typically it doesn't even matter what the b function is, you're just multiplying by 0 almost every time. So then for the I index, keep in mind that now if I is itself less than p minus 1, then what you'll have is that the overall derivative of the f function, differentiated I times, it's just going to be completely 0. Because the m index itself, m would be less than or equal to I, because it's an index running up to I, and I is less than p minus 1. So m certainly is not p minus 1, and that means the summation of everything is 0. And so that's why you'd have this expression here. And on the other hand, if I is greater than p minus 1, then the only term that counts is the term when m equals p minus 1. And so what you'll have is f of I evaluated at 0. This is going to be I choose p minus 1 times the p minus 1 derivative of a evaluated at 0, which we know is 1. Then times b, the I derivative minus the I minus p minus 1 derivative of the b function evaluated at 0. So we are summing a bunch of things together using the generalized Leibniz rule, but as it turns out, there's only one thing that counts, which is when this a function is differentiated p minus 1 times. And that's why you choose the little f function in the way that you do to begin with, so that you can break it up in this style, so that you have this a function, which is especially easy to differentiate, and then it doesn't matter how complicated b is, because it'll just kind of vanish. All right, so then overall, we have that capital F of 0, which is the infinite sum of all the derivatives evaluated at 0. So what this turns out to be then is it's just the sum starting from the index I equals p minus 1 and going up from there, because the first p minus 1 derivatives don't count. Basically, they're all zeros. And so we have this quantity I, choose p minus 1 derivative of the a function evaluated at 0. That's just 1, as we said. And then we'll have, again, the I minus p minus 1 derivative of the b function evaluated at 0. So if we just expand a few of these terms out to get an idea of concretely what we're summing here, the first term, when I equals p minus 1, we're going to have p minus 1 choose p minus 1 times, now notice the index for the derivative of the b function is going to be p minus 1 minus p minus 1. So in other words, it's just the 0th derivative, or the b function itself, evaluated at 0. And then plus, so the next one is going to be p, choose p minus 1, and times b prime of 0, then plus p plus 1, choose p minus 1, times b double prime of 0, and you get the idea. So you have these binomial coefficients, and then successive derivatives of the b function, starting with just the b function itself. Now we're going to observe the following. B of 0, this is not going to be a multiple of p. So it's not in PZ, whereas b prime of 0, b double prime of 0, b triple prime of 0, etc., all the derivatives, those are going to be in PZ, or in other words, they will be multiples of p. So why should that be true? So it's not obvious that that's true. We need to show those things are true. So we'll say why? Well, because what happens if we go to b of 0, so let's just go back to our b function for a moment. So this is the product of x minus 1 up to x minus n, all raised to the power p. Now when you plug in 0, you're going to have minus 1 times minus 2 all the way up to minus n, and that raised to the power p. So, because what happens here is b of 0, this is going to be minus 1 times minus 2 all the way to minus n, and that quantity raised to the power p. And in other words, this equals negative 1 to the power n times n factorial, and that raised to the power p. And what we're going to do is we're going to choose p, the prime number, to be greater than n. That guarantees that n factorial can't possibly have a factor of p involved, because again, p is a prime number. So then similarly, n factorial to the power p, or to any power, that is, also will not have a factor of p either. So as long as you make this choice, this is guaranteed to be true then, that b of 0 is not a multiple of p. So there's a lot of constraints on p right now. We have to make sure that it's bigger than C0, have to make sure that it's bigger than n, and so forth. But as long as we're just making sure that p is sufficiently large, then it'll satisfy all of those things. So we're fine doing this. Now, how about if we go to b prime of 0? Now we need to get a sense for what this is. We don't actually need to compute what this is explicitly. We just need to see that it is a multiple of p. So why is that? So going back up to our function again, you can see that, let's not differentiate the entire thing, but what we will do is we'll say b of x, so first of all, let's take u of x. This will be just the interior part. So x minus 1 times x minus 2 all the way to x minus n. And that means that we can express b of x as u of x to the power p. So the reason for doing this is that then you can differentiate using this u substitution for derivatives. And so b prime of x, that'll be p times u of x, and then chain rule says you multiply by u prime of x as well. Now, it doesn't really matter what u of x times u prime of x is. The point is we have this p out front now. And so this p is actually going to persist not only for this derivative, but for all the next, the successive derivatives. So b double prime of x, that'll be p times, again, it's the same number p here because it's a constant out front. And then you have to differentiate u times u prime, which we don't really care what it is. It's complicated. We'll just say p times something. But again, we have this factor of p here. And so similarly, b triple prime, again, you'll have a factor of p times some, even more complicated thing, but whatever. You're always going to have a factor of p. And also note that whatever's on the inside is going to be an integer because u, the u substitution type function that we made, that's a polynomial, and it's an integer polynomial. So when you plug integers into it, in particular when you plug 0 into it, which is the value we're concerned with, you're going to get an integer out of it as well. And so that reasoning filters all the way through from the u function to the b function to all the derivatives of it and all the way to the f function itself. You're just going to have some algebraic operations dealing with integers. So that's why you're definitely going to get an integer out of this. But anyways, so what we've just decided here is that b prime evaluated at 0 is going to be p times something. It'll be some integer, which we don't really know what it is, but we don't really care either, because it's some multiple of p. And so similarly, b double prime will be some multiple of p, and so forth. So what that means then is that if we go back to the entire sum, you see that since all the derivatives of the b function have a multiple of p, and keep in mind this is a finite summation, we don't know how far we're going, but it's finite because even though it looks like it's an infinite summation, we're dealing with polynomials, which will eventually zero out when you differentiate them enough times. So we can just factor a p out of everything, or at least out of the terms starting with the first derivative and going on to wherever the end so happens to be. So that shows that this overall summation of the derivatives with the associated binomial coefficients, that will have a multiple of p. So that itself is p times something. Or in other words, this is showing that that overall summation is a multiple of p. So what we have is this giant term of the summation of derivatives, that is a multiple of p, and then the initial function is, just b of 0 is not a multiple of p. And so therefore, what we can conclude is that this entire quantity that we're computing here, which keep in mind was capital F of 0, that is not a multiple of p, because if you add something which is a multiple of p together with something which is not a multiple of p, the overall sum is not a multiple of p. And that is exactly what we wanted to show for item 1. So we've finished with that item now. So lastly, we want to prove item 2, which is saying that the sum of the ck/fk's from k equals 1 to n is an integer which is a multiple of the prime p. So let's come back down here one last time to prove that item. And the structure of this part of the proof is going to be remarkably similar to the proof of item 1. So here we want to show that sum k equals 1 to n of ck/f of k is in PZ. And for the proof of this, it's going to here suffice to show that simply fk itself is a multiple of p. And we show that for all k equals 1 to n. So f of k is in PZ for all k. So just like in the proof of the prior part, we're going to compute f of k. And so this is going to be the sum, the infinite sum I equals 0 to infinity of all the derivatives evaluated not at 0 at this time, but at k instead. And so now, if we just use our function one last time, this is x to the p minus 1 times x minus 1 up to x minus n power p, and then that over p minus 1 factorial. And just like before, we're going to break the function up, although we're not going to break it up in the same way. This time, see, inside this x minus 1 to x minus n, at some point x minus k appears. And that's the part that we're going to isolate from everything else, along with the coefficient p minus 1 factorial. And then that'll be one function, so we'll call that c of x. And then the rest of it we will call d of x. And so again, we can express this function little f as a product of c times d. And the advantage of computing this is that this time the c of x function is very easy to evaluate at k. So again, using the generalized Leibniz rule, we'll have that the ith derivative at k, this is going to be the sum m equals 0 to I of the binomial coefficients I choose m times the mth derivative of c at k, and then times the I minus mth derivative of d at k. So just to be clear, we have that the c of x function, this is going to be x minus k to the power p over p minus 1 factorial. And for similar reasoning as before, what happens is that every time you differentiate this function, you always get 0, except in the special case when you differentiate exactly the degree of this little polynomial here that many times. And in that case, you'd end up with p factorial over p minus 1 factorial, or in other words, p. So just to write that all out, what we have is that the mth derivative of the c function evaluated at k, this is going to be equal to either one of two things. Either it'll be equal to p in the special case that m equals p, so the number of times that we differentiate is exactly the degree of the polynomial, or otherwise, if so we'll say otherwise, if m is any other number of times that we've differentiated, then we're going to end up with 0. And again, that's simply because if you differentiate less than p times, then x minus k, when you plug k in, you get a 0. Or if you differentiate more than p times, then you've made the entire polynomial vanish. So this gives us a tremendous simplification of the summation, and this also explains why we wanted the other portion of the little f of x function to be structured in the way that it was, so that we could do this simplification as well when we're trying to compute the derivative. So with this simplification, when you want to compute the ith derivative of the f function evaluated at k, one of two things is going to happen. So in the case that the index I is less than p, then that also means that the index m is going to be less than p, because the index m is running from 0 to I. So you're just going to have 0, because you're going to be summing a bunch of zeros together for a total sum of 0. And then on the other hand, if the index I is greater than p, then in that case, you're going to have exactly one term which is non-zero, and that term is going to be I choose p times the mth derivative of, the pth derivative of the c function evaluated at k, which is p, as we said above, and then times the d function differentiated I minus p times evaluated at k. So then overall, when you want to evaluate capital F evaluated at k, that's going to be the sum starting now from the index I equals p, and then going up from there, and that'll be of I choose p times the I minus pth derivative of the d function evaluated at k. And now notice that this term here, p, this used to be the derivative of the c function, now it's a constant. And so we can actually pull it outside the summation. And so if we just pull it outside like this, that shows you that we have p times some quantity here. And this quantity is going to be an integer because, again, we're working with integer polynomials evaluated at integer points. So we certainly have an integer, and now it's a multiple of p, so this quantity is in the integer multiples of p. So k was arbitrary in all this, so that means that this is true for all k, and therefore when you sum up the sum ck capital F of k from k equals 1 to n, then if every individual f of k, starting from k equals 1, if they all had a multiple of p, you can factor a p outside of that summation as well. And that shows you that this entire sum is going to have a multiple of p, and that is what we wanted to show for item 2. Okay, great. So really we've finished up the entire proof. Let's just summarize what we've done in this proof and throw it all together for the conclusion of the proof. So now that we've finished all three parts, let's just make sure we see how to throw everything together for the conclusion. So we said that e was a root of this polynomial we ended up calling it g of x, but it was the sum k equals 0 to n of ck x to the power k for some integer polynomial. So what this means then is that the sum k equals 0 to n of ck e to the power k, that equals 0. And then what we did was we said, well, we can say that e to the power k, this is can be equivalently written as a sub k plus epsilon sub k over b, where we quantified these values. So ak ended up being this capital F function evaluated at k, and epsilon ended up being some integral. It was e to the power k times the integral from 0 to k of e to the minus t times f of t dt, and b, this ended up being f of 0. But no matter what it was, we made this replacement for e to the power k in the polynomial equation, and so we were able to derive a new equation which had to be true. So we derived that the sum k equals 1 to n of ck f of k, and then plus initially c0 f of 0, and then also plus the errors, the sum k equals 0 to n of ck epsilon sub k, all that together had to be 0. But what we've done is that in item 1, we showed that this term was some integer which was not a multiple of p. Then item 2, we showed that this quantity here, it was an integer multiple of p. So then that means that this overall summation here of these two parts overall must not be an integer multiple of p. And in particular, what that means is that this implies that this is some non-zero integer. And finally, if that's a non-zero integer, then that means that this quantity over here had to be also a non-zero integer. But what we did was, for part 3, which is actually the first part that we did, we showed that this error term, or this modification of the error term, this actually went to 0 as you let p go towards infinity. So in particular, for a choice of sufficiently large prime, the absolute value of this quantity here was less than 1. So as long as you made a large enough choice for your prime p, which is always possible, then you get this contradiction that on the one hand we needed this error term to be a non-zero integer, but on the other hand it isn't, because it's a small error term. And that gives us our contradiction, and that is the true end of the proof. So we can put a little box here to indicate that we are done. And now that we've finished writing up the proof, let's go back to the slides one last time so that we can conclude the video. Okay, so here we are back at the slides for the final time. So we've already formally concluded the proof that E was transcendental, but let's just to wrap it up, demonstrate that it's how similar it is with the proof that E was irrational. So on the left we give a sketch that E was irrational, and on the right that E is transcendental. So the proof in both cases started off with assuming the opposite for contradiction. So to prove E was irrational, we assumed for contradiction that E was actually rational. That is, it could be represented as this ratio of integers. And then to prove E was transcendental, we assumed for contradiction that it was actually algebraic. And so we assumed that E would satisfy this equation here, some integer polynomial equation. It was a root of it, so it equaled 0. And then we made some approximation of E, or the powers of E. So in the case of irrationality, we said E was approximately capital E sub b, where this was the truncated Taylor series. And then on the right, for the transcendental case, we approximated the powers of E and by these rational numbers, a sub k over b. Now, in both cases, we could precisely say what E was, or the powers of E. So E was exactly equal to the first b terms of the Taylor series plus the infinitely long tail. So this was, in a sense, the error term in the irrationality case. And then for the transcendental situation, the powers of e were exactly equal to a sub k plus epsilon errors, epsilon sub k, all that over b. So the epsilons over b, those were our errors in the transcendental case. And then finally, with those expressions for e, what we did was we found a contradiction using the errors. So e minus e sub b in the irrationality case, we modified that by multiplying by b factorial. We showed that that was some quantity less than 1 strictly, but it was also a non-zero integer, and that was a contradiction. And then similarly, for e being transcendental, we showed that this sum here, this modification of the errors, was in absolute values strictly less than 1, and it was also a non-zero integer, which was, again, the contradiction. So while the details of both proofs, of course, differed, the high-level structure of both was really entirely the same, as you can see in this side-by-side comparison. So hopefully this gives a sense of the motivation for where the proof of e being transcendental would come from in the first place. It comes from modeling the proof of irrationality. So this is really the end, both of this video and of this mini-series overall. If you've been watching the first few parts, this is really just a recap of all 3 parts that we've covered now. Part 3 is what we've just been doing. But in Part 1, we discussed the structural aspects of these exponential and logarithmic functions, and that's where we defined e. It was defined as the exponential function evaluated at 1. Then it was in Part 2 where we gave the computational aspects of the exponential and logarithmic functions. We did so using Taylor series expansions for these functions. We also did some approximate numerical computations using approximations of the Taylor series. And we also discussed the relationship of e with compounding growth. And then finally, in this part, which is a bit independent of these other 2, it's really more of a bonus part than anything else. But here is where we proved that e is irrational and that it's more generally a transcendental number. So in particular, what we had to show is we defined algebraic numbers and transcendental numbers, and we showed that e met the definition of being a transcendental number. Typically in a basic real analysis course where the logarithmic and exponential functions might be formally introduced, these topics are given a bit of short shrift relative to how important they are. The exponential function especially is just ubiquitous in math. So hopefully going through some of these details gets you a bit more comfortable with exponentiation and these associated functions. But whatever your reason for watching these videos were, thank you very much for doing so.